Welcome back to First Python Notebook. This is Ben Welsh, still broadcasting live from Manhattan, USA. We're now ready to get into something really interesting, something we haven't covered yet so far, which is how to calculate your own statistic based on more than one data input. So far, we've been doing kind of groups and counts and sums where we take a single column and we analyze it to try to describe what's in there. But now that we've got assembled together our accident counts and our flight hour totals, we're ready for the first time to take two different data columns and put them together to compute a new statistic, an accident rate. So before we begin that, let's remind ourselves what's in our data frame. So after having done our reading in our data, after having grouped up the accidents to create an accident count per make and model, after having read in our survey data, after having cleaned both of those data sets so that they're ready to join, we have this nice and tidy table with 12 records in it, one for each make and model. And it has this one column that has the number of accidents for that make and model, and then another that has its total number of flight hours. These come from two different data sources, right? And we've brought them together to answer our journalistic question, which again is which make and model has the highest accident rate, and where does the Robinson 44 kind of fall in that calculation? And so to do this, it's actually now shockingly simple. And this is what can be a lot of fun about working with pandas and can make it very rewarding over time, is that once you have the data put in together and everything's in good condition, you can really quickly begin to run some pretty interesting analysis. And a common pattern with a lot of data journalism projects is you spend 95% of your time just getting the data. Like, remember, I waited months for the FOIA request for the flight hours. And then you spend a whole other chunk of time trying to clean the data, prepare it, to understand it, to interview people about what's in it, to find the flaws in it, and make sure that the warts don't ruin what you're trying to do. And then after all of that, the actual finding and the statistics you run at the end can often be done in just a few minutes, which can be a sort of strange sensation, but it really is the fruit or the result of all the work that you've put in there to get to that point. Now, in this class, we've kind of had a little bit of a head start because we started with data that was already in hand and ready to go. But so the payoff might not feel quite as sweet, but trust me, it's a little strange and quite interesting when it first happens to you. So to do this, all we really need to do, the mathematical formula for a rate, is just to divide the accidents number by the hours number. How many accidents per hour is our question, right? And as we remember from where we very began with Python, just taking the number 2 and dividing by 10, right, is how you write that simple math in Python. Number 1 divided by number 2. Well, it turns out you can do the exact same thing, except your numerator and your denominator are pandas columns or data frame series. And so if I strictly just take merged list, I do the index, and I call out that accidents column. So now I'm just saying I want you to take the accidents column and divide it by 10. Every number in that accidents column is then divided by 10. So we see the Robinson R44 number is 38, and down below it comes back as 3.8, right? And so a series is divisible by whatever you put on the right-hand side. And since in this case, we want to divide each one by its corresponding flight hours total, all we have to do is drop in the total hours column on the right-hand side. And so now we're saying take this series and divide it by that series. And the result is, boom, the accident rate for every make and model. It's just spit out here as one of these unattractive pandas data series that we need to kind of get into our data frame and tidy up. And so just like we can save the result of other operations as a column or overwrite them, we can create a new column. And so here is a trick we haven't done so far, which is I've started with my data frame and I've indexed it. But into the index, I put a column that does not exist. So we have here an accidents column and a total hours column. I'm saying, hey, data frame, make a brand new column and call it this. You could really call it anything, right? And into it, put the result of that calculation. So if I do that, and then I just ask it to print out the merged list again, we will see that we now have a per hour column right there along the side. Anyone who's written in an Excel formula and kind of pulled down the result of the formula across a whole column will realize that this is a very similar circumstance to that. It's just you're doing it in Python rather than with an Excel formula. So we've got our rate. Like an issue I see with this already as an editor is these numbers are kind of funky. Like what's going on here? We see after the number, we have this E negative 06, E negative 07. For anyone who doesn't know, those are a case of scientific notation. So whenever a number is a fraction that starts with a dot and then multiple zeros, dot 0.1, for instance, the number of zeros can be abbreviated in this kind of old school mathematical style to make it a little more legible on the front end. And so what this is saying is there's a large number of zeros ahead of this 9, and the real number is quite a bit smaller than 9.4, right? And the reason for that is if you look at the numbers, it makes a lot of sense. This helicopter only had one accident, but it had 1 million flight hours, right? And so the rate is very, very low. What we've encountered here is a problem that's very common when journalists try to measure rare events. You know, in the case of a murder or a homicide, or maybe even a coronavirus infection or any other thing that only happens to a small subset of the population, if you give people a rate based on strict division, the number can come back so small that it's very difficult to understand or to read. It's just not as legible to us as humans. The computer doesn't care, right? To the computer, the numbers are just numbers. But ultimately, we want to translate them into something that makes a little more sense to the average person, that could be said on television or written in the newspaper and be a little more conversational. And so one of the most common techniques for calculating rates on rare events is to do what's called a per capita rate. So when we calculate the accidents per hour, that's per single hour, right? But what you can do is you can say, well, what if we were to say we want to take some of those zeros off the result, and we want to say, well, how many accidents were there per 100,000 hours, right? Which has 5 zeros on it and would allow us to bring everything a little bit closer to a legible number. And then at the end of the day, we can say the per capita rate, or the number of accidents per 100,000 hours, is this easier to understand number. The exact same calculation is done for homicides when people say how many murders were there per 100,000 people. There's no reason that 100,000 is a better number than any other. It just tends to kind of work out in that it creates a legible figure. But all it is just sort of changing the math to not change the result, but just to make the result more legible and understandable, right? And so depending on what your rate is, it might make sense to be due per 1,000 people or per 10,000 people or per million people. It all kind of depends on the scale of the data that you're looking at. There's alternative ways of framing it too. With COVID, a lot of people discarded talking about rates on per capita basis and would instead sort of reverse the numbers around to talk about 1 in 10 people or 1 in 7 people. And that's just a different way of transforming the number, which actually stays the same underneath it all, but reporting in a way that's just attempting to try to reach the reader and make it more easily understandable. And so in our case, we decided to go with the per 100,000 flight hour approach, which, as we've just discussed, is a debatable kind of, way of framing. But we felt because it was so commonplace and because the FAA had used a similar, transformation of the numbers when they reported their own government-sponsored rating in the 1990s, we thought, well, we'll do the same thing they did, and that was commonplace in other forms of journalism, and just make sure that we're really as clear and transparent with our readers as we can be in that process. And so all that really requires is that you take the result of the division and you multiply it by the base. That's your adjustment. In our case, that's 100,000. And so I can take our merged list data frame. I can again index it, but I want to pull out that per hour column. And now I can just take that times 100,000. So if I take this column and I take every value is going to be multiplied by the fixed number of 100,000, we now have the per 100,000 flight hour rate. And so we see here that it's really the same numbers. It's just the zeros get shaved off and they're now stored and they're now come out as something that's a little closer to legible, 1.0, 0.4, etc. So I want to save that finally back into our data frame. So we merge list. I'm going to invent another new column. And this one I'm going to call per 100K hours. Again, totally debatable. This is just me inventing a new column and trying to come up with this concise and clear name for it. And so the first one was per hour. This one we'll call per 100K hours. And so now I run the result of that, and boom, we've got a legible rate that we've calculated all on our own that will ultimately, we hope, form the findings of our story. And we're going to get to that in our next chapter when we learn how to convert this data table of numbers into a sorted ranking that's ready to say who's number one, who's number two, who's number three, etc., and the kind of thing we could pass on to our fellow reporters and editors as a provisional finding to consider publishing in our piece.